Hi, and welcome to our second part on component-wise boosting. Here I'll continue discussing a couple of technical details of the algorithm that we didn't have time before. So I'll discuss a bit more how we handle categorical features, mainly focus on numerical stuff. Also talk a little bit about intercept handling. It's kind of also, special thing that's a bit discussion worthy. And then there will be a lengthy animation at the end where we run component-wise boosting on a more realistic data set, and we'll peek into the details of what happens as the algorithm runs along in terms of pseudo-residuals and reduced risk, and how the effects of the associated features develop. So let's maybe start by discussing categorical features. It's not super complicated here. So for categorical features, we basically have two options to model them through base learners. So either we can use one base learner to estimate all categories simultaneously. So here we would use a structure like this. We can do something like a one-hot encoding of our categorical feature, and then have like one parameter per category, and we directly fit this base learner, and it's just in competition with all of the other base learners in component-wise boosting, and it either gets added in if it reduces the SSE fit against the pseudo-residuals the most, or not. The other option is to kind of use one binary base learner per category. So each category gets its individual base learners. So I guess there's also usually the question for this first approach here, do we actually do a one-hot encoding? So like 0, 1 for each feature, or do we do this like G-1 encoding with the reference category? So here we usually use really one-hot encoding. So one parameter per category, because this is not really overspecified, and the reason is here because we don't use an intercept in that learner. And about intercept handling, I will talk a bit later in a few minutes here in the same session. So let's compare these two approaches a little bit. All of that's kind of somewhat obvious. It's not super clear which of these is better. So if we handle all of these categorical features in one like global base learner, then obviously the estimation is much faster. So we don't have to iterate over all of these different base learners. So if there's like a categorical feature with a lot of categories, we would add in capital G base learners. We have to iterate all over them, kind of bookkeep over them. This is much faster. We also can like directly estimate their parameters, because what we're basically doing is we're just like summing up the outcomes for that category and then like using the average value. You can kind of explicitly write down the solution for these. I guess we have to be a little bit careful here, because I'm not sure whether I should have put yi here. I mean, that's in the boosting algorithm, that's going to be the vector of pseudo-residuals. So I guess we could have also put an r here. And if the categorical feature is quite like high dimensional in the sense that it has very, very many categories, we might also want to add in a rich penalty into the learner. And I hope you still remember that we can then still solve the parameter estimation explicitly, analytically, by going from the normal equation to a version of the normal equations where we have the rich penalty added in. Okay, so the other option would be to handle everything individually. This would enable much finer selection of non-informative categories. So especially here for this first approach, right? And especially if we're not using a lasso penalty, which would make it computationally more expensive, and we cannot really analytically solve this anymore. Usually all of these categories here will have non-zero effects, right? We will usually not drive out uninformative categories from the model and from the effect of that feature. If we use individual base learners, uninformative categories might not be selected by the component-wise boosting procedure. So we kind of are exploiting this feature selection effect that I talked about in the previous session, and that would help us also to become sparse in the set of categories for that categorical feature. Again, there's a very, very simple explicit solution for our parameter estimation. Works basically as before, now just with a single category. but the fitting procedure is slower. So I guess if you really care about like also generating an understanding of which categories are important, and if you don't have too many of those, I guess the second approach here might be a bit nicer and convenient for you. If you have really high categorical features and want to have something that's a bit more efficient, model them in a single base learner and use this rich penalty term. Okay, a few comments about intercept handling. So that's also kind of a little bit special here. So again, there are two options. So one option is to kind of include a specific base learner for the intercept. So you just have like a constant function, and that gets also added into the pool, and you can adapt that in every single iteration. And then you would remove the intercept from all of the other base learners. Yeah? So they would all be, in a certain sense, zero mean. And that usually also means that we are centering our features in that approach. The second option would be that we keep the intercept in each, usually linear base learner, and then at the end aggregate them into a global one. But that just means like modeling everything as we've also done it before, and then just like extracting the intercept from all of the individual base learners and collecting them into a single one, so we can kind of, I don't know, read it off, and remove it from the individual base learners in post-processing. And that's basically it. I now want to end with a longer example here where we look at all of these different aspects of component-wise boosting a bit more in detail. So we have used the life expectancy data here. So that's a data set from the WHO, also available on Kaggle. I think we have simplified this a little bit here. So we are mainly looking at life expectancy as an outcome. So life expectancy in years, based on features like which country are we in, I don't know, Germany, Sweden, and so on, the recorded year. Maybe there's a year effect. And we're also looking at things like BMI, so body weight divided by height squared, and some measurements about adult mortality. And we'll run our component boosting with 150 iterations. We'll visualize that and see how which features actually get selected, how the base learner effects develop over time, and so on. So let's do exactly that. So at the moment we are at 0 iterations. We have nothing in our model. We have not selected anything. We can look at our empirical risk. I guess we are using a constant already because of the initialization. And at the moment we are at an empirical risk of 60. I'm pretty sure we are measuring that as, I don't know, either SSE or RMSE. And now what we are doing is, as always in gradient boosting, we are computing our vector of pseudo-residuals. And we are now iterating over all of our base learners. And you can see here the current partial feature effect. So this is when we collect together also explained this before, when we would collect all of the base learners together for a certain feature. And here I have only used univariate effects for each individual feature, and then we add them all together and plot the marginal effect. And because currently there's nothing in the model, all of our partial effects here are 0. There's like just one global constant in here, our global intercept that we have fitted in initialization. And you can now see here the candidate models that you can, first of all, you can see the pseudo-residuals here on the y-axis. And you can see which base learner, so in this case, I guess it's going to be mainly linear ones here that we are allowing ourselves to use. And you can see how the candidate model would look like if we would fit against the vector of pseudo-residuals and which SSE we would get. And if we now iterate over this, in the inner loop, we would now select the optimal one from these 4. Maybe remove a little bit of scribbling again. So let's see. I guess I could also see this. Well, I can see this very well also on this slide because it's marked nicely in red here. So for the feature country, you can also see here this apparently is now a categorical feature, and we are using this kind of combined global category handling that we discussed before, where we model the categorical features in this specific categorical feature in one base learner. You can also see here the estimated effects for all of these individual categories, based on the 0-1 encoding, and based on the formulas that we have discussed here in the slide set. And this actually now would be used as our first base learner that would be selected, and that drives down our empirical risk. So in this plot here, you can now see in what iteration which feature has been selected. So apparently country has been selected first. You can also see how the risk goes down a bit because we are again multiplying this with the learning rate, with the step length. So risk doesn't go down drastically, kind of do this gradually, step by step. And in the second iteration, probably exactly because of this, because we like using a moderate, smallish learning rate, we'll select country again. And after 5 iterations, we have in all iterations selected country and country and country. Risk has been driven down a bit. After 10 iterations, again, the same. After 15, we are still adding in country and modifying its effect. You can also see that these guys here kind of move a bit more closer to the center of the individual data clusters here for the individual categories. And if I use a smaller learning rate, this would happen even more. If I would use a larger learning rate, this would happen a bit more aggressively, and we might not add in country for so many iterations. Okay, fortunately, after 16 iterations, something more interesting happens. So now adult mortality for the first time has a smaller SSE, also smaller than country here again. And we now add that in. And you can now see also for all of the other features, we are still at effect 0. You can also see from this plot here, they haven't been selected. So if we would kind of stop modeling here, we will only have a model containing 2 features, adult mortality and country. And after 20 iterations, you can see country was touched a couple of further times, and we added in an adaptive step for mortality, and so on, and so on, and so on. You can see risk goes down even further. After 37 iterations, again, we have only used these 2 features. Now we are beginning to also add in year. You can also see that, well, I'm not sure I want to say that, but risk reduction is going to stagnate a little bit here. What you can also now do is can peek at out of sample data, can perform some form of early stopping, and if risk reduction would not be, relevant for you anymore, not large enough for you anymore, you could stop the model here, and you can also decide on, do you want more risk reduction or do you want a sparser model? So at the moment, the pool of available features here is small anyway, right? Because we constructed the example like that. So at the very least, you can see here that we have not selected the BMI here at all. So at least that feature would have been kind of cut out by the built-in feature selection. So I want to stop here, and we'll talk a bit more about the connection of component-wise boosting with respect to traditional GLM modeling, and a bit more about nonlinear and advanced stuff in the upcoming sessions.